You wake up in the morning. The light through the window is a little different than it was yesterday. Your phone says it's 7:12, not 7:11, not 7:10. Time, apparently, has moved forward. It feels so obvious that we rarely question it. Yesterday becomes today. Today becomes tomorrow. And that's that. But let me ask you something strange. What exactly do you mean when you say time moves? Does it flow like a river? Does it tick like a machine? Does it push the universe along second by second? Or is that just a story we tell ourselves because that's how it feels? Here's something curious. You have never once experienced time going backward. You've never seen a shattered glass leap up from the floor and reassemble itself. You've never watched smoke gather itself neatly back into a cigarette. You've never grown younger. Everything in your experience points one way, forward. And because of that, we assume this forwardness must be built into the fabric of reality itself. But is it? Imagine filming a simple event, a planet orbiting a star, a pendulum swinging back and forth, 2 billiard balls colliding on a smooth table. Now play the film backward. Would anything look impossible? For many of these situations, you wouldn't notice anything strange at all. The balls still obey the same paths. The pendulum still swings gracefully. The planet still traces its ellipse. Nothing in those motions screams, "This is wrong," which is unsettling. Because if time truly had a built-in direction like a one-way street, then reversing it should break something fundamental. But in many cases, it doesn't. So where does this powerful sense of forward actually come from? Let's step back from planets and pendulums. Think about your coffee. You pour it hot. Steam rises. You leave it on the table. 10 minutes later, it's cooler. You have never seen cold coffee spontaneously heat itself up while sitting in a quiet room. That would feel absurd, almost magical. And yet, if you zoom in far enough down to individual atoms, the tiny particles in that coffee are just moving, colliding, bouncing, according to simple physical laws. And those laws, astonishingly, don't really care which direction you call forward. The equations that describe motion, electricity, even much of modern physics, they work just as well if you replace time with negative time. Think about that carefully. At the deepest level we currently understand, nature's rules mostly don't insist on a preferred direction of time. And yet, your entire life depends on one. You remember the past. You do not remember the future. You can influence what happens tomorrow. You cannot influence what happened yesterday. Why? If the microscopic laws are nearly indifferent to time's direction, is less than #0, 5# is greater than, why is your experience so stubbornly one way? There's a deeper discomfort here. When you say time moves forward, you're not actually describing something you see. You don't see time flowing. You see change. Clocks tick. Shadows shift. Wrinkles form. But what you truly observe are configurations of matter rearranging themselves. So perhaps the real mystery is not about time itself. Perhaps it's about why change seems to have a direction. Why do some transformations happen naturally, while their reverses never do? Why does order seem to slip into messiness? Why does structure decay? Why does everything age? You might think the answer is simply, because that's how the universe works. But that's not an explanation. That's a restatement. Physics is not satisfied with that, and neither should you be. Here's the unsettling possibility. Maybe time itself isn't pushing anything forward at all. Maybe the arrow of time, that deep, irreversible flow you feel, emerges from something more subtle, something statistical, something hidden in the enormous number of microscopic details we never see. And if that's true, then time's forward march is not a fundamental commandment of nature. It is a consequence, a pattern, an emergent feature of a universe that began in a very peculiar state, but we're not ready to go there yet. First, we need to confront a deeply uncomfortable fact. The laws that govern the smallest pieces of reality are almost perfectly happy running backward. So the real question is no longer, why does time move forward? The real question is, why does it look like it has to? And that's where the mystery truly begins. Let's perform a simple experiment. Imagine you're watching a silent film. On the screen, two billiard balls glide across a perfectly smooth table. They collide. They scatter apart. Nothing surprising. Now reverse the film. The balls roll backward. They meet. They separate in precisely the opposite direction. Does anything look impossible? No explosions. No violations of common sense. No cosmic alarm bells ringing. If I hadn't told you it was reversed, you might not even notice. That's peculiar. Because if time truly has a built-in arrow, a fundamental this way only rule, then reversing time should produce nonsense. But in this case, it doesn't. And here's the deepest surprise. The equations that describe those billiard balls, Newton's laws of motion, work perfectly well, forward or backward. If you replace time TTT with negative TTT, the mathematics shrugs. It doesn't object. It doesn't prefer one direction over the other. This isn't just a trick of billiard tables. Planets orbiting stars, same story. If Earth orbited the sun in reverse, following the exact mirrored path, gravity wouldn't protest. Electromagnetism is less than #0.25 hash is greater than, also mostly symmetric in time. At the microscopic level, the fundamental interactions of particles don't carry little arrows stamped on them saying forward only, which creates a serious puzzle. Because your experience of reality absolutely does. You remember yesterday. You anticipate tomorrow. Causes precede effects. Eggs break before they scramble, not the other way around. But if the basic rules don't distinguish past from future, where does this overwhelming asymmetry come from? Let's try another film. A pendulum swings from left to right. It slows. It swings back. Play it backward. Still plausible. Now imagine a planet tracing its orbit. Reverse it. Still fine. So far, nature appears completely indifferent to which direction we call future. That's unsettling. Because we've built our entire psychological framework on the idea that time has a direction baked into the universe itself. But physics, at least at this level, whispers something very different. It says the laws don't care. Now you might object. Sure, billiard balls are simple, but real life isn't. Exactly. Let's complicate the movie. Picture a glass sitting on a table. It slips. It falls. It shatters on the floor. Now reverse that. Shards leap upward. They assemble midair. The glass lands gently back on the table. That looks absurd. Instantly, you know something is wrong. But here's the catch. At the microscopic level, every fragment obeys Newton's laws. Every atom collides, rebounds, and follows deterministic rules that are time-symmetric. If you could reverse every single velocity of every atom at the exact instant after the glass shattered, the equations predict that the shards would indeed reassemble perfectly. No rule would be violated. So why don't we ever see that happen? Not once. Not in all of recorded history. The deeper you look, the stranger it becomes. It's not that physics forbids reversal. It's that reversal seems astronomically unlikely. And now we're touching the edge of something profound. Maybe time's arrow isn't about laws. Maybe it's about probability. Consider the glass again. When it shatters, there are countless ways for the fragments to scatter across the floor. Millions upon millions of microscopic configurations. But there are very, very few arrangements in which all those atoms line up precisely to form an intact glass. The difference is staggering. One tiny region of possibility corresponds to glass. An enormous region corresponds to shattered mess. And nature, it seems, overwhelmingly drifts toward the larger region, not because it must, but because it's vastly more probable. This is the first crack in our intuition. Time's direction may not be imposed by the laws themselves. It may emerge from statistics, from the simple fact that there are far more ways for things to be messy than to be orderly. If that's true, is less than #0, 5# is greater than, then the forward motion of time isn't a fundamental push. It's a tendency, a bias toward what is overwhelmingly likely. And that raises an even deeper question. If time's arrow is statistical, then why did the universe ever begin in a state orderly enough for entropy to increase in the first place? Why wasn't it already maximally scrambled? Why was there any room for time to move forward at all? Now, we're no longer talking about billiard balls. We're talking about the entire cosmos. And to understand that, we need to confront a law that quietly governs everything from broken glasses to dying stars. A law that doesn't shout, but never fails. The second law of thermodynamics. And that's where the real story begins. Let's start in the kitchen. You pick up an egg, smooth, fragile. You tap it on the edge of a bowl, the shell cracks, the contents spill out. A few stirs of a fork, and the clear separation between yolk and white disappears. Now imagine the reverse, a fully scrambled egg in a pan, yellow and white perfectly mixed. And suddenly, without any intervention, the molecules politely reorganize themselves. The yolk gathers, the white separates, the shell reconstructs. You drop the pan. It feels impossible. But here's the unsettling truth. At the level of individual molecules, nothing in Newton's laws forbids it. Every molecule in that egg obeys simple rules of motion. Collisions, forces, energy exchanges, and those rules, as we've seen, are almost perfectly time reversible. So why don't scrambled eggs ever unscramble? This question haunted physicists in the 19th century. They had beautiful equations describing motion. They had precise laws governing heat and energy, and yet they noticed something strange. Heat always flows from hot to cold, never the other way around. Ice melts in warm water. Warm water never spontaneously forms ice cubes at room temperature. There was a pattern here, an asymmetry, and that pattern became known as the second law of thermodynamics. Now, the second law is often summarized in a single, slightly ominous sentence. Entropy always increases. But that word entropy sounds mysterious, almost mystical. So let's strip away the mysticism. Entropy is not about chaos in the dramatic sense. It's not about destruction. It's about counting. Yes, counting. Imagine you have a box divided into two halves. On the left side, you place all the air molecules. On the right side, nothing. That's a very specific arrangement. Now remove the divider. The molecules bounce around randomly. Very quickly, they spread out evenly across the entire box. You never see them spontaneously drift back to one side. Why? Because there are vastly more ways for molecules to be spread out evenly than to be clumped neatly in one half. This is the key insight. A low entropy state is one with very few possible microscopic arrangements. All molecules on the left side of the box? Very special. Molecules evenly distributed everywhere? Overwhelmingly common. So when the divider is removed, the system doesn't decide to become disordered. It simply evolves into what is statistically most likely. And that almost magically defines the arrow of time. The scrambled egg represents an enormous number of microscopic configurations. The intact egg represents a tiny, tiny subset of those possibilities. So when you crack the egg and stir it, the system moves from a highly specific arrangement to one of astronomically many possible arrangements. Reversing that process would require every molecule to coordinate itself with absurd precision. Not impossible according to the laws, just unimaginably improbable. And here's the subtle but profound shift. The arrow of time is not enforced by the microscopic equation. It emerges from probability, from the simple arithmetic of large numbers. When you have trillions upon trillions of particles interacting, the overwhelmingly likely direction of change is toward higher entropy. Not because the universe prefers messiness, but because there are more ways to be messy than to be neat. This is both humbling and astonishing. Time's forward march, the aging of stars, the cooling of coffee, the breaking of eggs, may be nothing more than statistics at work. No cosmic clock pushing events ahead. No fundamental forward gear in reality. Just probability unfolding. But now something even stranger appears. If entropy always increases, that means it must have been lower in the past. And if it was lower in the past, then the universe itself must have started in an extraordinarily special, low entropy state. Think about that carefully. The reason you remember yesterday instead of tomorrow, the reason eggs scramble but never unscramble, may trace all the way back to the conditions at the birth of the cosmos. The arrow of time may not be written into the laws of physics. It may be written into the initial conditions of the universe. And that shifts the mystery to an entirely new level. We are no longer asking why eggs break. We are asking why the universe began in a state ordered enough for breaking to even be possible. Why wasn't everything already maximally mixed? Why was there room for entropy to increase at all? That question is far deeper than it first appears, because it suggests that time's direction is not a local phenomenon in your kitchen. It is a cosmic one. And to follow it, we have to zoom out, far beyond eggs, beyond coffee cups, beyond even planets. We have to ask about the beginning, and that is where the story becomes truly astonishing. Let's slow down for a moment, because what we just said is almost too simple. Time moves forward, because probability says it should. That sounds suspiciously modest. Surely something as profound as the flow of time cannot reduce to arithmetic. And yet that's exactly where the trial leads. So let's look more carefully. When you describe a system, a cup of coffee, a room full of air, an egg in a pan, you usually talk about it in broad strokes. Hot or cold, mixed or separated, intact or broken. Those are what physicists call macro states. They're the big picture descriptions. But underneath each macro state lies an astonishing number of microscopic possibilities. Take a simple example. Imagine flipping 100 coins. If all 100 land heads, that's one very specific arrangement. But if roughly 50 are heads and 50 are tails, there are an enormous number of different combinations that produce that same overall description. Half heads, half tails corresponds to vastly more microscopic arrangements than all heads. And if you shake the coins randomly, what are you likely to get? Not all heads. You'll almost certainly get something close to half and half. Now replace coins with molecules. Replace 100 coins with trillions upon trillions of atoms. The difference in numbers becomes almost incomprehensible. A low entropy state, like all the air in one corner of a room, corresponds to a tiny fraction of possible arrangements. A high entropy state air, evenly distributed, corresponds to an astronomically large fraction. So when molecules bounce around randomly, they don't aim for disorder. They simply wander. And wandering in a landscape of possibilities almost guarantees you'll land in the overwhelmingly large regions. That's entropy increasing. It's not a force. It's not a push. It's geometry. The geometry of possibility space. And here's the key realization. The arrow of time is nothing more than the direction in which entropy increases. That's it. When entropy increases, we call that the future. When entropy was lower, we call that the past. Time's direction is defined by this gradient. But notice something subtle. The microscopic equations themselves do not contain this gradient. They allow motion either way. It's the initial condition that matters. If you begin in a highly special, low entropy configuration, then random motion will almost certainly carry you toward higher entropy. But if you began already in maximum entropy, complete equilibrium, nothing interesting would happen at all. No structures, no stars, no eggs, no you, just a dull, uniform fog of particles drifting aimlessly. So now the mystery sharpens. The second law doesn't say entropy always increases from every possible starting point. It says, given a low entropy beginning, entropy will most likely increase. That's a very different statement. It means time's arrow depends entirely on where you started. Think about that carefully. If the universe had begun in total equilibrium, perfectly scrambled, there would be no arrow of time, no thermodynamic gradient, no distinction between past and future. Change would still occur microscopically, but nothing meaningful would emerge. The fact that we observe a strong arrow of time tells us something profound. The universe must have started in an extraordinarily low entropy state, not moderately low, extraordinarily low. And here's the astonishing twist. When we look at the early universe through telescopes, through cosmic background radiation, we find something that initially looks chaotic, a hot, dense plasma. But thermodynamically speaking, it was remarkably smooth and ordered, which means the universe began in a highly special configuration, a configuration balanced on an improbable ridge in possibility space. And ever since then, entropy has been climbing. Stars form and burn. They radiate heat into colder space. They eventually die. Galaxies evolve. Coffee cools. Eggs scramble. And you grow older, all because the universe started in a state that allowed entropy to increase. The arrow of time, then, is not something imposed by the laws. It is something inherited from the past, a relic of the beginning. But this creates an even deeper puzzle. Why was the beginning so special? Why was entropy low at all? Why wasn't the universe born already maximally disordered? That question pushes us beyond thermodynamics and into cosmology. And when we follow it, we discover that the arrow of time may ultimately be a clue, a fingerprint left behind by the birth of the universe itself. And that realization changes everything. We've arrived at a very uncomfortable place. Time flows forward because entropy increases. Entropy increases because the universe began in a low entropy state. So now the real question is staring at us. Why was the beginning so special? Let's rewind, not in violation of physics, but in imagination. Back past the formation of Earth, past the birth of the Sunday, past the first stars, past galaxies themselves, until we reach what we call the early universe. Hot, dense, blindingly energetic. At first glance, it looks like chaos, a seething plasma of particles and radiation. Surely that must be maximum disorder. Surely that must be high entropy. But here's the twist. Entropy isn't just about temperature. It's about structure. It's about how matter is arranged, especially under gravity. And gravity changes the story in a very surprising way. Imagine spreading sand evenly across a flat surface. Now imagine piling that sand into clumps and dunes. Without gravity, uniformity might seem like the messy state, but with gravity, things are different. Gravity wants matter to clump. Stars form because gas clouds collapse. Galaxies exist because matter gathered together. Black holes emerge when matter collapses even further. Under gravity, a uniform distribution of matter is actually highly ordered. That's the counterintuitive part. The early universe was incredibly smooth. When we measure the cosmic microwave background radiation, the faint afterglow of the Big Bang, we find the temperature variations were tiny. 1 part in 100,000. That smoothness is extraordinary. It means matter was spread out with almost perfect uniformity. And under gravity, that's an extremely low entropy configuration. Think about that. The universe began not in a chaotic mess, but in a delicately balanced, highly special state. Like a pencil standing perfectly upright on its tip. Balanced, precarious, improbable. From that smooth beginning, Gravity slowly amplified tiny fluctuations. Matter began to clump. Stars ignited. Galaxies formed. Black holes devoured. Entropy increased dramatically, and the arrow of time strengthened. But the question remains, why was it smooth? Why was the universe born in such a low entropy gravitational state? Because statistically speaking, that's astonishingly unlikely. If you were to randomly choose a possible configuration for the universe, almost all of them would look wildly irregular, dominated by black holes, highly clumped, already at enormous entropy. Instead, we got something exquisitely ordered. Why? Now, here's where honesty is important. Physics does not yet have a complete answer. We have theories about cosmic inflation, a rapid expansion in the earliest fraction of a second that may explain the remarkable smoothness. But even inflation requires certain initial conditions. So the mystery retreats further back. It doesn't disappear. It deepens. And this is the astonishing realization. The reason your coffee cools, the reason eggs scramble, the reason you remember the past instead of the future, may ultimately trace back to the boundary conditions at the birth of the cosmos. Time flows forward because the universe began in a state that allowed entropy to increase. If the beginning had been different, the arrow of time might not exist at all, or it might point the other way, or there might be no meaningful distinction between past and future. That's staggering. It means the forward motion of time is not built into the equation. It is a historical fact about our universe, a relic of its origin, like a ripple still spreading from an ancient disturbance. And now, something even more personal comes into focus. Your memories, your aging, your sense of cause and effect, all of it depends on that ancient low-entropy beginning, which means the arrow of time is not just a cosmic phenomenon, it is intimate. It lives inside you. But how exactly? How does entropy connect to memory? Why do we remember the past, but not the future? To answer that, we have to turn from galaxies and black holes to brains. And that's where the mystery becomes deeply human. Let's bring this down from galaxies to something much closer. You. You remember yesterday. You remember what you had for breakfast. You remember a conversation. You remember being younger, but you do not remember tomorrow. And that feels so obvious that it hardly seems worth mentioning. Of course we remember the past. Of course we don't remember the future. But why? If the microscopic laws of physics are nearly time-symmetric, why is memory so stubbornly one-directional? Here's the crucial idea. Memory is not abstract, it is physical. When you form a memory, something changes in your brain. Neurons fire, connections strengthen, chemical gradients shift. A physical record is created. And creating a physical record always involves an increase in entropy somewhere. Think about taking a photograph. You point a camera at a scene. Light hits the sensor. But in order to store that image, the camera must consume energy. Heat is generated. Entropy increases. A record of the past is written into matter at a thermodynamic cost. The same is true in your brain. To remember something, your brain must rearrange molecules. It must burn energy. It must increase entropy in its surroundings. And that's the key. The formation of memory is itself an irreversible process. You remember the past because the past has left physical traces, footprints in sand, ink on paper, neural connections in your cortex. These traces exist because entropy has increased. They point backward towards states of lower entropy. But there are no physical traces of the future because the future's higher entropy states haven't happened yet. There is nothing to record, nothing to imprint, nothing to remember. So the psychological arrow of time, your sense that yesterday is fixed and tomorrow is open, is a consequence of the thermodynamic arrow. Memory depends on entropy increasing. If entropy were not increasing, memory would not exist. And without memory, the very idea of past and future would dissolve. Now this is subtle. You might think causality, cause preceding effect, is fundamental. Strike a match, it lights. Push a glass, it falls. But at the microscopic level, the equations don't strictly distinguish cause from effect. If you reversed all particle motions, the effect would appear to cause the cause. The laws would still work. What makes causality feel one-directional is entropy. Effects leave traces. Causes are conditions of lower entropy that evolve into higher entropy states. We interpret the lower entropy configuration as before, the higher entropy configuration as after. And that interpretation becomes our experience of time. Now pause for a moment. This means your sense of moving through time, your memory, your anticipation, your feeling of flow, is deeply connected to the universe's low entropy beginning. If the cosmos had started in equilibrium, there would be no increasing entropy, no irreversible record making, no memory, no arrow of psychological time, perhaps no conscious observers at all. That's astonishing. It suggests that the flow of time is not something happening to you. It is something emerging within you as a consequence of thermodynamics. You are a structure that can only exist in a universe far from equilibrium, a temporary pocket of order riding the upward slope of entropy. Your very awareness depends on the arrow of time, which means the question, why does time move forward, is also the question, why do we experience reality the way we do? But there is one more twist waiting for us, because even after everything we've uncovered, entropy, probability, memory, modern physics introduces an even stranger perspective. According to Einstein's theory of relativity, time may not be flowing at all. It may simply be another dimension. Past, present, and future laid out together in a four-dimensional structure called space-time. If that's true, then what exactly is this now that seems to be moving? And how does an arrow emerge in a universe where all moments may coexist? To answer that, we must step into the geometry of space-time itself. And there, the mystery becomes almost philosophical. Up to now, time has felt like a river, flowing, carrying us forward, entropy rising as we drift along. But Einstein quietly removed the river. In the early 20th century, when Albert Einstein developed relativity, he changed not just physics, he changed the meaning of time itself. According to relativity, time is not a universal ticking clock. It does not flow the same way everywhere. Two observers moving differently will measure different durations between the same events. Clocks run slower at high speeds. Clocks run slower near massive objects. Time stretches. Time bends. It becomes woven together with space into something unified space-time. And here's the part that unsettles people. In relativity, the distinction between past, present, and future is not absolute. What is now for you may not be now for someone moving at a different speed. The idea of a universal present dissolves. There is no single cosmic moment that everyone agrees on. Imagine the universe not as a movie playing frame by frame, but as a completed film reel. Every frame already exists. Every event, from the birth of the stars to your next heartbeat, is simply located at a different coordinate in space-time. This picture is sometimes called the block universe. In it, time does not flow. It simply is. All moments coexist, laid out like points on a map. If that sounds disturbing, it should. Because if all moments exist equally, then what is this feeling of moving from past to future? What is this relentless forward march? From the block universe perspective, the arrow of time cannot be a fundamental feature of space-time geometry. Space-time itself is symmetrical. It contains earlier and later regions, but it does not privilege one direction over the other. There is no built-in forward arrow etched into the fabric, and yet entropy still increases. Stars still burn out. Eggs still scramble. You still age. So how do we reconcile these two pictures? On one hand, relativity suggests that all moments exist. On the other, thermodynamics tells us there is a strong asymmetry a gradient from low entropy to high entropy. Here is the subtle resolution. The arrow of time is not written into the geometry of space-time itself. It is written into the distribution of entropy within space-time. Think of space-time as a vast landscape. Across that landscape, entropy is not uniform. There is a direction from the early universe's smooth, low-entropy state toward the future's increasingly clumped, high-entropy state. That gradient defines the arrow, not geometry, not motion, but boundary conditions. In the block universe picture, the early universe sits at one end of this gradient, low entropy, highly ordered. As you move along the time dimension away from that boundary, entropy rises. Observers like us can only exist in regions where entropy is increasing, because memory, structure, and life depend on that increase. So even if all moments coexist in space-time, our conscious experience traces a path along the entropy gradient. We interpret that gradient as flow. We experience it as becoming. But fundamentally, it may be a structural asymmetry, not a moving present. That's a radical shift. It suggests that the sensation of time flowing is not something happening to the universe. It is something happening within certain subsystems, like brains embedded in a universe with a low entropy boundary. The universe itself may simply be a four-dimensional structure, but because entropy was extraordinarily low at one temporal boundary, there is a preferred direction in which complexity unfolds. And along that direction, memories accumulate, stars ignite, life evolves, and we feel carried forward. But notice something profound. Nothing in the fundamental equations of relativity demands that entropy be low at one end. That fact lies outside the equations. It is a condition imposed on the solution, a historical fact about our cosmos, which brings us to the final and deepest question. Why was there such a boundary at all? Why did space-time begin in such a special configuration? Because that single fact, that one astonishingly improbable condition, is the reason time has an arrow. And without it, there would be no forward, no memory, no evolution, perhaps no story at all. To understand that boundary, we must look directly at the birth of the universe. And when we do, the answer is stranger and more humbling than we expect. We've peeled away layer after layer. Time doesn't flow because equations demand it. It doesn't move forward because clocks push it. The microscopic laws are mostly indifferent. Relativity doesn't enforce a universal now, and yet entropy increases. Memories form. Eggs scramble. You grow older. So everything points back to one extraordinary fact. The universe began in a state of astonishingly low entropy. That's the pivot. That's the hinge upon which the arrow of time swings. Let's be clear about how strange this is. If you imagine all the possible ways the universe's matter and energy could have been arranged at the beginning, almost all of them correspond to extremely high entropy, clumped, collapsed, dominated by black holes. Instead, what we observe through the cosmic microwave background, through large-scale structure, is that the early universe was extraordinarily smooth, tiny fluctuations, incredible uniformity. Under gravity, that smoothness is rare, staggeringly rare. So rare that some physicists have compared it to balancing a pencil on its tip, except the pencil is the size of the observable universe. And yet, that's how it began. Why? We don't fully know. There are ideas. Cosmic inflation, a rapid exponential expansion in the earliest fraction of a second, may help explain why the universe looks so uniform today. But even inflation requires initial conditions. The mystery retreats further back. It doesn't disappear. And here is the humbling part. The arrow of time is not explained by deeper dynamics, at least not yet. It appears to be a consequence of a boundary condition, a fact about the edge of space-time, a constraint at the beginning, which means the reason time only moves forward may not lie in a force, not in a mechanism, but in the simple historical fact that the universe started in a very special way. Think about the implications. If the early universe had been in equilibrium, maximum entropy, there would be no thermodynamic gradient, no irreversible processes, no structure formation, no stars to shine, no planets to cool, no chemistry complex enough for life, and certainly no brains to ask questions about time. The very possibility of complexity depends on that initial improbability. We exist because entropy had room to increase. And time feels like it flows because we are carried along that gradient. In this view, the future is simply the direction in which entropy is higher. The past is the direction toward the low entropy boundary. We call that boundary the beginning of the universe, the Big Bang. But perhaps it is more than just a hot explosion. Perhaps it is the anchor point of time's arrow, a special edge in space-time from which all becoming emerges. And here is the final twist. Nothing in the fundamental laws forces the universe to have such a boundary. It could, in principle, have been different, which means the forward motion of time is not inevitable in every conceivable universe. It is a feature of ours, a fingerprint of our cosmic origin. So when you feel time passing is less than #0, 5# is greater than, when you watch a sunset and know it will not reverse, when you remember yesterday and cannot remember tomorrow, you are experiencing the aftermath of an extraordinarily improbable beginning. Time moves forward because the universe started in a state from which forward was overwhelmingly likely, not because it had to, but because of how it began. And that realization changes the question. Instead of asking, why does time flow? We might ask, why did the universe begin in such a special state? That question reaches beyond thermodynamics, beyond relativity, perhaps even beyond physics as we currently understand it. But one thing is clear, the arrow of time is not written into the laws like an instruction. It is written into the history of the cosmos, and every second that passes is a reminder of that ancient boundary. The forward motion you feel is not the ticking of a universal clock. It is the unfolding of probability from an improbable beginning. And that is far stranger and far more beautiful than the idea of time as a simple river carrying us along. Because it means the flow of time is not a given, it is a story written at the birth of the universe. And you are living inside its consequence.